So I thank you organizers
It's perfect.
Bringing luminescence thermometry to a higher level. Before I start my talk, I want to show this slide again. I think you've seen this yesterday. I'm not sure how much of the presentation you got along. My first Viovilov symposium was in 2001 in Kazan, and I have really good memories of that symposium. It was a wonderful place. After the symposium, because my flight was leaving late, I was taken to a dacha with Boris Malkin on the Volga River. It was really wonderful. We had vodka for breakfast, which is not common in the Netherlands. It was a wonderful Russian banya, where I think I remember Sergei Nikitin hitting me with twigs and branches. A great experience, a great introduction to Russian culture. Then it took some time in 2013, again, a Viovilov symposium in Kazan. Then St. Petersburg in 2015. This actually is not a picture from 2015, but a year before, where I met Alexander Kapliansky when I visited St. Petersburg. 2018, Yekaterinburg, where we see a picture here with Marina and Mike and Sergei Viovilov. And Konstantin Ivanovsky, who showed us around, brought us to the Europe-Asian border together with Mike. Wonderful visits. I'd never been to Moscow, so I was really looking forward to this year's Viovilov Symposium to finally be able to visit Moscow, but unfortunately that is not possible. The Viovilov Symposia, of course, are in honor of the great Viovilov, but here and at many other occasions that's also been done, I like to remember Sergei Viovilov, the son. Sergei was a good friend and a great scientist, and this is a picture taken during that same visit where I met Alexander Kapliansky in his nice corner room at the Joffe Institute. Here he's speaking as a chair of the DPC conference, and here chairing the International Program Committee of the DPC. Sergei was more than a brilliant scientist. He was a kind and wonderful colleague, and he served our luminescence community in many different ways. Of course, as chairman of the DPC, and in 2 weeks we will have next DPC conference in Wrocław in Poland. Also, he was a member of the International Program Committee of the ICL, and as editor of the Journal of Luminescence, he's really done wonderful job, including this nice booklet, The Luminescence Legacy, that he edited. So Sergei will be deeply, deeply missed by our community. Now let's go to the talk. I will start with an introduction explaining what luminescence thermometry is and how it can be used. Then I will discuss some basics. It's a booming field, luminescence thermometry, but a good theoretical background was lacking, and we've done some work to get a better foundation in the temperature range and sensitivity when you realize Boltzmann equilibrium for one type of luminescence thermometry, quite important, and what is the temperature accuracy. And then I will discuss 3 applications: catalysis, microfluidics, and temperature mapping, where we use our high temperature nanoprobes to measure luminescence temperature. So let's first discuss what is luminescence thermometry. It's a technique where you measure temperature by just measuring a luminescence spectrum, and from changes in the luminescence spectrum as a function of temperature, you can deduce what is the temperature. And that can be in the luminescence lifetime. In that case, you need pulsed excitation, and you look at the luminescence decay time as a function of temperature. And typically, when you go from cold, low temperature to high temperature, the luminescence decay time gets faster. And by measuring the luminescence decay time, you can deduce what is the temperature of your luminescent probe inside the material or the sample where you want to measure the temperature. Then you can also measure luminescence spectra by continuous excitation, measure the spectrum, and then the intensity can be a parameter. And typically the intensity drops when you increase the temperature, or you can see a peak shift as a function of temperature, or you can probe the peak broadening. But the most widely used technique for luminescence thermometry is to measure a luminescence intensity ratio between 2 peaks that changes as a function of temperature. And the nice thing of that is that that is independent of alignment of your sample, because there's internal calibration. Just measuring the ratio of two peaks gives you the temperature. As an example, I here have the spectrum of erbium-3 plus in sodium yttrium fluoride nanocrystals. And this is the energy level scheme of erbium-3 plus, or at least some of the energy levels, ground state 4i15 Then there's around 20,000 wave numbers, the 4s3 excited state, and just above there, the 2h11 states. And the energy difference is about 700 wave numbers. Now, at room temperature, thermal population of the 2h11 level already gives rise to some emission from the higher level to the ground state, that is this emission, and the dominant emission is still from the lower excited state 4s3. But then when you raise the temperature, see that emission from the higher level starts to increase relative. This is all scaled to the 4s3 level emission, and it goes up and up and up. And by measuring the temperature, the ratio of intensity from the higher level and the lower level, you can deduce the temperature. And the nice thing of lanthanides, of course, is that they have very sharp line emission, so you can very accurately isolate the temperature from the emission intensity from the higher level and that from the lower level. And if there's Boltzmann equilibrium between the two levels, which means that the relaxation between the two excited states is much faster than population decay from either state, then the intensity ratio from the higher level to the lower level scales with the exponent of the energy difference over kBT. And then when you plot the natural logarithm of I2 over I1 versus 1 over T, you get a straight line where the slope is delta E over the Boltzmann constant. So that's very nice. And when you want to measure in different temperature ranges, you can use different pairs of coupled ions from lanthanides, and well, there's many energy levels of the lanthanides. So you can really choose what set of coupled energy levels, lower and higher level, you choose for a specific application. So the lanthanides are really ideal probes for luminescence thermometry. And a lot of work has been done. As I said, it's a booming field. In the last 10 years, many reviews, many papers have come out. This is a nice review by Eva Hemmer, Vetrone, and also Artur Betnakiewicz, Dani Jacques, Wisław Strenk, Miloslav, Luis Carlos, all experts in the field. But what I said, what was still lacking is a good theoretical foundation, so that's where we have done some work. What is the best choice of thermometers? There's two figures of merit that are important to luminescence thermometry. One is the absolute sensitivity, and the absolute sensitivity is defined as the change in the intensity ratio per temperature interval dt. But what is more widely used is the relative sensitivity, which is again the change in the ratio per temperature interval dt divided by the intensity ratio. And of course, what you want for a good thermometer is that the ratio changes as much as possible in a small temperature interval, so you get a large change in the ratio to accurately distinguish between different temperatures. This is a very comprehensive paper, and it was work done by Marcus Suta, and here you see Marcus Suta at his PhD defense. I was in the committee, and in Germany they have this strange habit of making some big hat that reflects all things that happened in their life during the PhD ceremony. So there Marcus is. We looked at the theory of luminescence thermometry, tried to decide several things. We looked at the kinetics, the thermodynamics, and also what is the optimum temperature range for a specific energy gap between the two levels. So what you have to realize there, and this is the most illustrative plot, is what you want is you want a large change, delta n, in the relative population between 1 and 2 per temperature interval. So this change in population between the higher and the lower level, the relative change, is still pretty high here, and that is higher when you have a large energy difference. Then when you have a large energy gap between the two levels, then the change in temperature will relatively get more population in the higher level. When you are at a really high temperature or a very small gap, well, then the two levels will be equally populated 50-50, and change in temperature will not change the population. So you want a relatively high gap to have a good delta n over the total number of emitters to get more population at a higher level where you increase the temperature. At the same time, you need to detect emission from the higher level. And if the energy gap is really high, there's no population higher level, and you have no signal from the higher level. So then the response from your luminescence thermometer is 0. So here you start to get population from the higher level. And what you theoretically deduce is that the optimum temperature gap is that the energy gap between the levels should be between 2 times kBT, the temperature that you want to measure, and 2 plus the square root of 2, so 3.41 times kBT. This is the optimum window where you have the best response of your thermometer based on still having a large change in population as a function of temperature, but also having appreciable population of the higher level to get a measurable signal. So that's the temperature range and sensitivity. Then the second important aspect that is often forgotten is you need Boltzmann equilibrium. The relaxation between the two excited states has to be much faster than population decay from either state, otherwise the intensity ratio does not follow Boltzmann statistics. So what you need is that the coupling, both the emission of phonons to go from the higher level 2 to the lower level 1, but also the absorption of vibrations to go from 1 to 2, which is the slower process, both have to be much faster than radiative decay or any population decay process of those levels. And you cannot take that for granted, especially when you're at the lower temperature range, the onset of your optimum temperature window. Depending on the host that your ion is embedded in, you may or may not have Boltzmann equilibrium. So we did again some modeling, and what we see there is if the two levels, the two excited states are coupled, can be coupled by one high energy vibration, then you reach Boltzmann equilibrium much easier than where you need 2 or 3 or even 4 vibrations. The reason being that if you need 4 phonons, 4 vibration, it's a fourth order process. This energy difference between the two levels has to be picked up by a transition from the 0 vibration level to the 4th vibration level, or you have to occupy the 4th vibrational level of the local environment to absorb from level 1 to level 2. And the higher order the phonon process, the lower the probability is. So that was theory, where you see high phonon frequency levels. Hosts will help to establish Boltzmann equilibrium. Then we also did experiments, and we compared 2 types of hosts: a low phonon energy host, an oxide, where the maximum vibrational energy is about 500 wave numbers, with the phosphate and the borate, where we have 1250 or even almost 1500 wave number phonons. And we looked at the europium-3+ ion. It's my favorite ion. Very nice, simple energy level scheme. And we looked at the thermal equilibration between the 5D0 level and the 5D1 level, about 1700 wave numbers higher. And then there's phonon emission to go to 5D1 to 5D0, and that scales with n plus 1 to the power p, where p is the number of vibrations that you need to bridge the gap, and n is the phonon occupation number that increases when you raise the temperature. And the phonon absorption, that scales with n to the power p, again the phonon occupation number to the power p, the number of phonons that you need. And our theory predicts that if p is higher, if you need more phonons, then the equilibration will be slower, and that's exactly what we observe. So when we look at the intensity ratio as a function of temperature, and you see that for the yttrium oxide europium, initially when you increase the temperature, note here's a scale of 1 over T, so this is low temperature, this is high temperature. When you increase the temperature initially, the phonon emission speeds up, populating more of the 5D0 level. So even though you have a higher temperature, the intensity ratio decreases because you get more emission from the lower level, because this relaxation goes faster. But then at even higher temperatures, the phonon absorption rate picks up, and you start to realize Boltzmann equilibrium. And in this regime, you have the linear relationship, the logarithmic of 1 over T, Boltzmann equilibrium. But the onset temperature is really high, 560 Kelvin. But when you look at the higher phonon frequency lattices, the phosphate and the borate, because you can bridge the gap by only 2 phonons, the onset temperature is much lower, much easier reaches fast relaxation between the two levels. It's 160 degrees lower. So the host lattice where you put your luminescence thermometer in is really crucial for the performance. And a high phonon frequency host helps to extend the temperature range where you have Boltzmann equilibrium. Then there's other factors that also play a role. The distance, if your ligands are closer to your luminescent ion, like in sodium lutetium fluoride compared to the sodium lanthanum fluoride. Also, the relaxation gets faster. The photon coupling is stronger when you have small distances. And what we also realized, what is really important, is the type of transition that couples the two levels. If it's an electric dipole transition, the relaxation, it couples this electric dipole transition on your vibrational environment. The coupling is much stronger, the relaxation rates are much faster than when the two levels are coupled by a magnetic dipole transition. Then the relaxation is slower, and you see that the onset temperature is much higher. If you compare hosts with a similar gap, similar number of photons, you see that for the praseodymium or the europium with magnetic dipole transition, the onset temperature is much higher than for dysprosium or erbium, where the two levels are coupled with electric dipole transitions. And then finally, also the dopant concentration is quite crucial. As an example, I here have a very well-known temperature probe, neodymium 3+. There the 4s3 halves and the 4f5 halves levels coupled by an energy gap of about 1,000 wave numbers are used. The nice thing is that the emission and the absorption is in the infrared, and for biological samples, infrared light penetrates deeper into the biological samples, so then it's nice to have infrared emission and absorption. Those two levels are coupled by a magnetic dipole transition. Delta J is 1, and the predicted onset temperature is our theory where you expect thermal equilibrium, Boltzmann equilibrium, is just around room temperature. And indeed, for 0.1% neodymium, you see that starting at room temperature, you get a nice straight line Boltzmann equilibrium. However, when you increase the concentration, there's not only radiative decay from the two levels, but there's also very fast cross-relaxation, where one neodymium ion excited state transfers part of its energy to a neighboring neodymium ion, and especially this resonant cross-relaxation process, 4i5 halves to 4i15 halves on one neodymium, 4i9 halves to 4i15 halves on a neighboring neodymium, really depopulates those excited states. And again, the condition for Boltzmann equilibrium is that population decay should be much slower than the relaxation, the photon relaxation that couples those two levels. And when we induce an additional population decay process, this cross-relaxation, you see that there's no Boltzmann equilibrium until really high temperatures, almost 500 Kelvin rather than 300 Kelvin. So also the concentration of your luminescent ions is crucial whether or not you get Boltzmann equilibrium. Then the third basic that we studied, the temperature accuracy. Quite important. In the end, what you want to know is how accurate is the temperature that I measure. And that's what we say in the field is the $1 million, about 60 million ruble question, knowing how accurate your measurement is. And the clue is, and I was very happy with the talk yesterday by our present chair, Sapatsky, who measured very small Faraday rotations, and he said intensity is crucial. If you have more intensity, more signal to noise ratio, that improves your accuracy. And the same is true here. In a lot of papers in the literature, the people who do luminescence thermometry, they measure the relative sensitivity, and from that they calculate what is the best accuracy that you can realize if you have, well, infinite intensity, and then they say, well, we can have a 10 millikelvin accuracy, but in the end, you need a signal. You need a good signal to noise ratio to get accuracy. So last year we had a symposium in our NanoTB Tech European Consortium, in which we discussed in luminescence thermometry we trust, but can we? So we did some modeling on the temperature accuracy, and just as yesterday with the small Faraday rotation shot noise or Poissonian noise, the statistics of your photon counting determines the accuracy. And it's very simple simulation. If you assume that you have in a peak intensity 100 counts, then the Poisson statistic tells us that there's about the square root of 100 is 10 counts variation in that intensity. So when you simulate your spectrum, well, depending on the statistics, you get a rather noisy spectrum. And then when you simulate many different spectra, the emission from the higher level, emission from the lower level, determine intensity ratio that is varying because of the noise statistics, you get a rather large spread in temperature. But when you increase the intensity by a factor of 10, so you have 1,000 counts in the peak, then the accuracy really increases. So in the end, the temperature accuracy, delta T, is 1 over the relative sensitivity times the variation in your luminescence intensity ratio over the luminescence intensity ratio. And that is really important. So that's the theory. And then we also did experiments. Again, our favorite erbium ion. We measured emission spectra with a CCD camera. You can very quickly measure them. And we did that 200 times. So we had our sample at room temperature, or a bit above room temperature, and we measured spectrum, determined the intensity ratio of the 2H11 halves over the 4 halves emission, deduced the temperature, and then we saw that, yeah, the inaccuracy, the variation in the temperature that we get is determined by Poisson or shot noise. And then when we did it at different temperatures, the red points are the temperature accuracy that we measured based on a large number of experiments. And well, the best delta T that we got was about 0.2 Kelvin. And when you increase the temperature, then because the relative sensitivity for the erbium thermometer decreases, the error also increases, and it very nicely follows our simulation. So that shows that, just like yesterday with the small Faraday rotations, that shot noise, Poissonian noise, determines the accuracy that you can realize. So it's not just the relative sensitivity that is important. Signal really matters. You have to make very bright, strongly luminescent probes to get a good temperature accuracy. And then there's many other aspects. There can be background subtraction errors that affect your accuracy. Also important is wavelength-dependent light scattering or wavelength-dependent light absorption. If you have your 2 emission peaks from the higher level and the lower level, and one wavelength is scattered more than the other, or one wavelength while traveling through your medium is absorbed more than the other, then the ratio that you measure further away is not the intensity ratio as it was emitted by your emitter. So the temperature that you calculate from your measured intensity ratio is not the temperature at your sample. There can be additional overlapping signals that can affect the ratio. There can be calibration errors. If you look in the literature, the values for delta E for the same erbium ion and sodium fluoride varies quite a bit, depending on what temperature range people use for the fitting. There can be spectral correction errors, and also, and I will come to that in the end, photonic effects, the Drexage effect, can play a role in changing the intensity ratio. So the big guys who've done the work here are Thomas van Swieten and Freddy Rabau. They will also present their results at the ICOM coming up next week in Belgrade, and the DPC in Wrocław the week after. So then let's go to some applications. Catalysis, microfluidics, and temperature mapping. As I mentioned, a lot of work in the past has been done on luminescence thermometry in biological systems, where you work from room temperature, maybe 50 or 60 degrees centigrade. We extended that to higher temperature ranges, where we wanted to measure temperatures in catalytic reactors up to 600 or 800 degrees centigrade, in microfluidic system, where you also go to really high temperatures or can go to high temperatures, and also temperature mapping in microheaters. What we use for that is the most widely used temperature probe, sodium fluoride erbium ytterbium upconversion nanocrystals, where you excite the ytterbium at 980 nanometers, get energy transfer to ytterbium, and in a two-step energy transfer process, you populate the 4 level, get nice green emission from the 2H11 halves level, the higher level, and the 4 halves level. And the nice thing is of this upconversion, you excite in the infrared, you get visible emission from your luminescent probes, but not from the environment. There's no upconversion from the organic molecules or whatever is around there. So you have a really nice background-free signal that helps to accurately determine those intensities. And of course, it's good to mention here that upconversion was discovered independently by François Ozel and Feofilov and reported in 1966. So for our catalytic reactor, we made nice core sodium fluoride, ytterbium, erbium nanocrystals, and you see there's very good synthesis methods. We have very homogeneous, about 30 nanometer or 20 nanometer nanocrystals. Then to be able to allow them use them at high temperature, and that's something that we did, is we coated them with a silica shell. And that makes them temperature stable When you do not do that, then the particles deteriorate or agglomerate at high temperatures. So that silica shell is really crucial for the high temperature sensing that we want to do in catalytic reactors. Then we put them in extrudates where there's a catalyst inside for whatever catalytic reaction you want to do. Then you put them in a quartz tube where you then put the reactants over to have the catalytic reaction happen, and then you have it in an oven. So this is the final setup where here we have our quartz tube with our catalyst with the temperature probes inside. And then we had methanol to olefin reaction. We did that together with the catalysis group in Utrecht, Bert Weckhuizen, where the methanol is by the catalyst inside polymerizes to make an olefin. And then we probe the temperature through this slit at different heights in our catalytic reactor. And this is how it looks like. So our probe, and that is, we do that with fiber optics. So you have a fiber optic like this, where the central fiber is connected with a 980 nanometer laser. So this is the fiber optic that you aim at your reactor. You can probe at different heights. And then it's split off, and the central fiber is connected with a 980 nanometer laser, and the other 6 surrounding fibers, they collect the emission that is emitted. So you excite 980 nanometers, the emission comes off, and you probe it with one of those nice compact CCD cameras. So then very easily with this fiber optics, you can probe the emission spectra at any height in your catalytic reactor. So you feed with methanol, the catalytic reaction, you analyze the product with gas cross-thermometry, but then at different heights you can probe the temperature, and then you see that at the top the temperature really rapidly increases, and then also slower decreases, and in the middle the increase in temperature is slower, and the drop is faster, and at the bottom the increase is even slower, and the drop is equally fast. And that shows that in those catalytic reactions you can really, as a function of position, probe in a high temperature regime with our luminescent nanoprobes, probe the temperature. The second system that we used was microfluidics. Microfluidics is also a booming field where you have microchannels of 10 to 100 micrometers, where you have reactants flow through those channels, and while they flow through the reactor, they can react and lead to a product. And that can be a very nice continuous flow process to reproducible synthesize chemicals. The problem is, what is the temperature inside the channels? You cannot stick a thermometer in those 10 micrometer or 100 micrometer channels. So it's really difficult to measure the temperature inside those micro reactor channels. Typically there's the temperature sensor at one or maybe more spots on your microfluidic device, but what's the temperature inside the channels is not easy. There you can again use our luminescent nanoprobes. If you feed in your reaction fluid, if you include luminescent nanoprobes, then with a confocal microscope or just a microscope setup, you can focus your excitation at different places wherever you want inside the microfluidic channel, collect the emission, and then know what the temperature is at that specific spot in your microfluidic reactor. So we use different types of microfluidic reactors in connection with the University of Twente. And as an example of one here, this is a microfluidic reactor where we fed the channels with a fluid with our sodium fluoride, ytterbium, erbium nanocrystals. And there is a temperature sensor at this position in the microfluidic reactor. And we measure the temperature at that same spot where also the temperature sensor is to calibrate and to see if the luminescent spectra indeed gave the correct temperature. And we also measured it at the spot further on in the downstream in the microfluidic reactor. This is what we measured at the temperature sensor spot, and the temperature at the spot was exactly the same as the platinum temperature sensor, only 0.3 degrees difference. Then when we looked at the spot further on, the red points are what we measured from our luminescence spectra. You see that there's a pretty good deviation of almost 6 degrees centigrade between the set point that we arranged with this sensor and the actual temperature inside the microfluidic channel. So that shows that we can use luminescence thermometry to measure temperatures using our nanoprobes in those very small microfluidic channels. Similar thing we did for a very simple chemical reaction. We fed an acid, hydrochloric acid and ammonia, and it went through the channel, the microfluidic channel, and then at the end of the channel we focused our laser beam and measured the emission spectra, and there we can see when we put the flow on, the temperature increases, and when we turn the flow off, the temperature decreases, the temperature rise of about 15 degrees due to this exothermic acid-base reaction. Then the third and last application, mapping the temperature with micrometer precision of microheaters. Those type of microheaters, about 200 micrometers big, very small, are used for at synchrotrons when you want to do X-ray scattering of a sample and want to see what happens at high temperatures, or in electron microscope, TEM, where you also sometimes want to go to elevated temperatures. They use those very small microheaters, typically a few hundred micrometers big. It has a molybdenum heating spiral, and the temperature calibration is usually done by measuring the resistance of the molybdenum wire. But the question is, what is the temperature distribution over the microheater? And how fast does it fall off towards the edges of the microheater? So there we again used our nanocrystals. So we made our sodium yttrium fluoride nanocrystals. We drop casted them on top of the microheater. These are nanocrystals, 32 nanometers in size, nice homogeneous size distribution. We did the calibration curve, and then we measured with a confocal microscope the emission spectra for any spot on our microheater. So here, just for one spot, from right spot, we show the emission spectra. So for that square micrometer of sample on top of the microheater, you measure this emission spectra, emission from the 2H11 halves, 4 halves level, calculate intensity ratio, deduce the temperature, and this is what we got. And that was rather peculiar. It was just at room temperature, so you expect a homogeneous temperature distribution, no changes, but what we observed is that there was, what we calculated, a lower temperature on top of the spiral, and that's surprising. The reason is the Drexage effect, interference from the reflective surface of the molybdenum wire. And that's something that has never been realized in the field of luminescence thermometry, but you can have those interference effects. When you have your emitter close to a reflecting surface, light of different wavelengths shows interference effects, and that can increase or decrease intensity depending on the distance of your emitter to the surface. And that will be different for different wavelengths. So that means that the intensity that you measure with your probe further on is affected by a difference in interference for your emission at 520 nanometers from the 2H11 halves level and emission from the 4 halves level. So the intensity ratio that you measure here is not the intensity ratio as is actually emitted by your sodium yttrium fluoride erbium probes, but it's affected by this type of interference effect that are different for the 520 nanometer emission and for the 540 nanometer emission. So you have to correct for that. And that correction factor increases when the intensity from the higher level increases, so it increases temperature. But we is mainly Freddy Rebau and Thomas van Swieten, were able to develop a correction protocol, and then when you correct this intensity profile that you base on the intensity ratios as they are measured by the correction, then you get a nice homogeneous distribution, but you really have to take into account this photonic effect. And then you can also calculate the temperature at different spots. Then you see that for higher temperatures, indeed, at the edges, the temperature starts to fall off, and that also scales with the model that was developed by Dan Solution, that makes those microheaters. So that brings me to my conclusions. I hope I've shown that luminescence nanothermometry is a promising method for remote temperature sensing and temperature mapping. It's really nice to remotely, from a distance, be able to measure temperature. Second, the selection of temperature probes, you really have to do some theory, some careful consideration, look at the sensitivity, the brightness, bright probes are better. Check if you have realized Boltzmann equilibrium in the temperature range that you're probing it. And also photonic artifacts can be very important. The relative sensitivity is not the only or most important factor. Temperature accuracy also requires bright probes. High luminescence intensity is crucial. And overall, I hope I've seen that there have to be new developments to bring luminescence to a higher level by making high temperature sensing probes, getting higher accuracy, widening the temperature range, and getting a higher spatial resolution. Then I'd like to thank some people. I'd like to thank Thomas Oswiete, Roman Geitenbeek, Freddy Rabau, Marcus Soete, Detjaju, Anna Kaczmarek, Els Bladen and Bert Wekhuizen for contributing to this work. The Nano-TBTech Consortium, a really nice European consortium where we worked with the Vinca team, Miroslav Dramikanin, Luis Carlos, Lukas Macianek, and Artur Bernakiewicz, Daniel Jacques and Bruno Faviani. Wonderful team. And finally, I also like to thank Marina Popova for inviting me to speak at this meeting. I remember the first time I met Marina. It was at my first conference ever. I was a PhD student in the group of Jos Blasse, Jos Castle. A wonderful conference with all the big names, Hans Gudel, Frank Imbush, Alexander Kaminsky, but also Marina was there. And I remember the beautiful high-resolution spectra of the holmium, the lithium yttrium fluoride, where they observed the difference, whether it was lithium-6 or lithium-7. And Marina has really been an inspiration for me and for the field for the 34 years after my first conference. So thank you, Marina. And then I also want to congratulate both Marina and Boris for this very high and well-deserved recognition. And thank you all for listening. Thank you.
Thank you very much for a wonderful presentation. Please, questions?
Yes. Oh.
Thank you very much for this beautiful talk. I would like to inquire, did you estimate the spatial resolution of these thermometers?
Yes. Yeah. Again, the spatial resolution is determined by intensity, by the brightness of your probes. But for the latest experiments that I showed on this micrometer, we can focus down our confocal microscope to 1 micrometer, and from 1 square micrometer spots get sufficient signal to measure the luminescence spectra. And again, their artifacts can be a problem because if you want to measure on a small spot, 1 square micrometer, you need to really focus your laser, get enough intensity. But then if you pump your upconversion material too high, you don't only get 2 photon upconversion, but also 3 photon upconversion. You get emission from a higher level that has emission to the 4. I certainly have that overlaps partly with your green emission, so you also have to correct for that. But yeah, we can go down to almost the diffraction limit of 1 micrometer.
Thank you.
Welcome.
A comment and a question.
May I? Okay, Marina, first.
May I speak?
Yes, Marina.
Yes,
Yes.
Marina.
Andreas, thank you very much for very interesting presentation and for remembering our old meetings. I would like to comment that so the ideas of luminescence thermometry seem to be very obvious and simple. Andreas showed us that it is in fact not such a simple thing to measure the temperature accurately and reliably. I have a question. Andreas, you spoke mainly of the high temperature measurements, but
Yes.
Do you see some application where the measurement of cryogenic temperatures would be desirable?
Yes, very good question, Marina. And actually, we're already using them. One thing that you can use there is the different crystal field levels. For example, gadolinium. If you look at your 6p7s level, it's split in lower and high crystal field components. That splitting is typically 10 or 20 wave numbers. And we just sent some samples off to another group where they have a cold finger cryostat, and they're not sure if the temperature that they measure with the resistors that's in the copper block is also actually the temperature of the sample, because they see it seems to be higher. So by putting there your luminescent thermometer, measuring emission spectrum, we can actually measure what is the temperature at the spot of my sample. And yes, so we also published an article recently using gadolinium, the crystal field levels for the low temperature regime. Then there's the 6p5s level for higher. So using multiple energy levels in different temperature regimes from 10 Kelvin to 500 Kelvin, you can probe the temperature. But yeah, it's a very universal probe where you can, and that's why the lens knives are so nice. It's a sharp line emission with small space levels, larger levels. You can, in every temperature regime, find the right couple of levels. As long as they are thermally coupled by Boltzmann, you can measure over the, from 4 Kelvin to, 1,000 Kelvin or even higher. Yeah, good point.
Yeah. Oh, thank you.
Okay, may I ask a question? So, Andries, thank you very much for excellent presentation and also for contribution to the symposium.
Yeah,
so,
thank you for the flexibility to arrange it at this time.
So, my question is about thermometry and mapping on the sub-micrometer scale. There is one more candidate for such kind of thermometry. It's nano and micro diamonds with some colored centers. Could you please comment and maybe your opinion, what is better and in what cases and so on? So some kind of comparison.
Yeah. The NV centers in diamonds also have a very nice, strong temperature dependence. And they can also be used. It's a similar technique, and I think the reported accuracy of the NV centers in diamonds is even better, but you don't have the same flexibility as with lanthanides. So there's one specific temperature range where it can be used very well, but it's only one luminescence center, the NV center. But yes, they've reported millikelvin accuracy with those NV centers in diamonds. So they can also be quite useful. And
also about your nanoparticles, do you know any applications in temperature mapping, for example, in live cell with your nanoparticles? Is it possible or not?
Yes, we have not done that ourselves in live cells, but I know group in Australia, they've put them in cells and then add a specific linker to mitochondria, and they could measure temperature raises in mitochondria depending on the local environment of the cells, whether they killed the cells or put them under stress. So that they can have good spatial resolution by just coupling the nanoparticles to mitochondria, but in the end they measure a larger space to get enough signal. But by putting specific probes that link to specific places in cells, then they can measure what happens in cells at that specific place. But they cannot just focus the beam on one mitochondria and measure temperature there, because then you just, you boil your cell.
Thank you very much.
Okay, any more questions?
Могу ли я задать вопрос на русском?
Okay.
А вы переведете?
Okay. May I ask a question in Russian?
Yes, that's fine. Maybe it's nice to know. Yesterday also George Blaser was mentioned.
With translation.
Spoke very good Russian, but I do not.
Yes.
Мне очень понравился ваш доклад по этой теме. Вы, наверное, хорошо знаете литературу по измерению температуры по люминесценции, люминесцентным методом. Я хотел спросить, вот вы упоминали метод измерения по времени затухания люминесценции. Кто является первым автором этого метода? Кто имеет патент на этот метод? Можете ли вы сказать?
I don't know about paid patent. I know that one ion that is used quite widely is chromium 3+. For chromium 3+, also in Ruby, but in many other systems. Of course, Ruby was studied extensively by Feophilov. You have the doublet E level. Just above there's the 42 level. At low temperature, you have emission from the doublet E, millisecond lifetime. at high temperature, you start to suddenly populate to 42, and the lifetime really decreases quite rapidly.
Ну, я ничего не понял. Можете перевести кратко?
Marina, can you translate? I didn't understand everything. Actually.
Yes, it was something happened with sound. So, Andreas, can you repeat once more your reply?
Yeah, so the question is about the lifetime.
About who invented the method of measuring the temperature by decay time?
I do not know who reported that first time.
Нет, не знает кто. Yes.
But I do know that a very famous system where that has been observed is Ruby, the chromium 3 plus, where you have the chromium 3 plus level, above that a 42. And then when you raise the temperature, at low temperature, you have millisecond emission from the doublet E. When you raise the temperature, you thermally populate the 42, and the lifetime goes down. So that's
Ну, это известно очень хорошо для рубина, что расщепление Е-состояния, вот люминесценция с этих двух уровней, и время очень сильно зависит от температуры. But do you know if anybody has a patent for this method? I suppose you do not.
I do not know.
Пора заканчивать мой вопрос. Я еще уточнить хочу. У меня есть патент на измерение именно температуры по времени затухания люминесценции 1973 года. Может быть, это первый патент?
In 1973, the participant who put this question, unfortunately, I do not see him. He has got a patent for measuring the temperature by measuring the decay time.
Yeah.
Maybe it is the first patent, but maybe it is. I suppose it's not the question to Andreas.
No, but that's interesting.
Yeah. Okay.
Thank you. Any more questions?
Mm-hmm.
No more questions then.